In this problem, we have a simple frame. We have two members pinned together here at, let's call it point C, and also the frame is supported at point A and B. We have two pin supports, and we need to solve for the support reactions at pin support A. Now, if we treat the frame as one system, so let's do a really simple free body diagram like this. If we treat it as one system, and we draw the free body diagram, we have 200-pound force right here at point A. Because we have a pin support, so we have AY and AX. Point B, we have BY and BX. At this point, you realize that we only have one free body diagram for 2D rigid body. Therefore, we can only write 3 equations, and we can solve for only 3 unknowns. But here, as you can see, we have 4 unknowns. This is BX. So if we proceed from this point, we cannot solve for all unknowns. Yes, we might be able to solve some of them. However, if you realize that, well, we can break the frame into components and draw the free body diagram for each of the component member, yes, we can do that. So we have free body diagram of AC, which is pinned at both ends. So we have AY here and AX, and CX and CY. But then we draw the free body diagram of BC. Here we have BX and BY. Here we have the applied 200-pound force. But at point C, we will have the action and reaction of CX and CY. They are not technically not action and reaction. These two members are connected through the pin. So these two forces are actually action and reaction with the forces on the pin, and then these two forces are also action and reaction with the forces on the pin, and these forces are actually in equilibrium. But in a simplified view, we can treat them as action and reaction. Therefore, you can write the same force as long as they are in the opposite directions. So what happens now is that you have 2 free body diagrams. So 1 free body diagram, 3 equations. 2 free body diagram, 6 equations. So we can solve for 6 unknowns. And here we have AX, AY, CX, CY, and BX and BY, 6 unknowns. So we can solve for all 6 of them. So that's definitely doable, but it's not the best way. So at least you can solve the problem with that approach. But the best way is to recognize that this member AC is a 2-force member. So if it's a 2-force member, then even though we do not know what the forces are at point A and point C, we know that the line of action of the 2 forces must be along the orientation of the member, and they must be opposite in direction, same in magnitude. So same line of action, same magnitude, opposite direction. So they can either be like this, or they can be like this. Only 2 possibilities. So if you recognize that, let's say it is like this. This is the case. This is how the forces are on member AC. Then, now we draw the free body diagram of member BC. So again, we have our BX and BY. Again, this is the applied 200-pound force. Now, at this point, this force must be in action and reaction with this force. Therefore, this force must look like this. Therefore, now you see that on this free body diagram for member BC, we only have 3 unknowns. We have F, BX, and BY. And this F right here let's call it FAC, is what we're looking for. So these three forces are of the same magnitude, same line of action. Therefore, from this free body diagram alone, we only need to set up one equation, which is resultant moment about point B. Because remember, we only need to solve for the support reaction at point A. Therefore, resultant moment about point B, Bx and By do not have moment about point B. We have negative 200 because the 200 pound force is creating clockwise rotation. The moment arm for the 200 pound force is this much, that's 3 feet. And then we have FAC creating counterclockwise moment about point B. The moment arm is this much. And this distance right here equals to, from here to here, that's 2. So this distance right here equals to 2 times cosine 30 degree. That equals to 0. So from this one equation, we can solve for FAC, which equals to 346 pounds. And that is actually the answer to this problem. So compared to the previous approach that I demonstrated, you can see that if you recognize AC is a two-force member, because forces can only be applied on 2 points on this member and there's no moment. So if you recognize AC is a two-force member, you will know the line of action of the forces acting on this member. And then from there, you know the direction of this force because of action and reaction. And then you can set up only one equation and solve for what you're looking for. So as you can tell, this greatly simplifies your calculation procedure.